Hello everyone, welcome to part 2. I'm going to draw a little track here just so that we can get some of our conceptual knowledge and turn it into concrete knowledge. Alright? So we're going to have this hill here, okay, and we're going to imagine we put a ball at the top of the hill and we hold it there, right on the edge. So if we were to let go, it would start rolling down the hill, okay? But we're not. We're just going to hold it there for right now. We're going to look at it at different points. First, we're going to look at it at point 1. Point 2 is going to be in there. We're actually going to look at that third. We're going to look at point 3 here. So after it rolls down that hill, you know, it's going to have picked up a lot of speed. So it's going to be moving. All right, it's going to be moving as it goes down the hill too. All right, so that's going to be point 3. All right, so let's talk about point 1. Let's say we know that the mass of this object is 2. So, you know, the mass is 3 kilograms. Let's say we know something else. Let's say we know that the height of this hill is 20 meters. Okay? And then let's say we also know some other stuff, but we'll get to that in a bit. All right? So, just knowing the mass and the height of this object, we know at the beginning, we can calculate what the initial conditions are. So there's this total energy, which we talked about. Total energy never changes. Okay? So there's a total energy at each one of these levels, at T1, T2, and T3. Okay? And they never change. Total energy of this system never changes. Okay? No matter which level it's at. All right. So at T1 is equal to, remember the total energy is equal to the potential energy plus the kinetic energy. Okay, so up here where you're holding it, when you're holding it still, the kinetic energy is 0. So the total energy right here is equal to the total potential energy. All right, and that's given by the formula of mass times acceleration due to gravity times height. Okay? In this case, that's going to be equal to 3 times 9.8 times 20. Right, I'm going to pull out my calculator here. Say 3 times 9.8 times 20. That's equal to 588 joules. All right, so that's the total energy at the start here. Okay. So now, instead of going right to number 2, we're going to make a conceptual leap here, and we're going to go right to number 3. And you'll see why I did that in a second. So number 3, the total energy is the same, okay, and it's still equal to the potential energy plus the kinetic energy. Right? We know that the total energy never changes. So that total energy right here, that's equal to 588 joules. We also know that when here at place 3, down here at the bottom, the height is 0. So this potential energy goes to 0. Right? And then, without ever having to do any kind of calculation, then we know that the kinetic energy here at the bottom at location 3 is equal to 588 joules. That's the conceptual leap. All right. I want to try to make it smaller so that I can. Nope, that's the wrong one. Try to make it smaller. There we go. All right. So that is the conceptual leap that I was talking about. So now let's go back to the middle one. Let's say that I knew that that height. Say I knew what that height was. So, chart 2, let's say it's halfway down. Say I knew that that height was 10 meters. Well, we know that the total energy is equal to the kinetic energy, or the potential energy, plus the kinetic energy. That total, we know is 588 joules. We knew that because it never changed. The potential energy is given by the simple formula that we used before. So the potential energy in this case is going to be equal to mass 3 times acceleration due to gravity, 9.8, times 10, because now it's at a height of 10. All right, so that's 3 times 9.8 times 10 is equal to 294. Right, 294 joules. Right. Now you might be saying, well, how do we find the kinetic energy? Because we don't know how fast it's going just from the information that we're given. Well, we have an equation with just one unknown. So we just solve for the kinetic energy. We subtract, we take 588 minus 294, and that was half the height, so it's half the energy, and we find that the kinetic energy is equal to KE2 is equal to 294 joules. Okay, so now we've calculated the kinetic energy and the potential energy for all three of these locations. But now you might say, well, I want to know how fast it was going. How fast? What was V2, right? Because we know that the formula for kinetic energy is equal to 1/2 mass velocity squared. Okay, so let's look at KE2. We know that it's 294 joules. 1/2. We know the mass is 3, and we want to know what the velocity is. Well, we just solve. We have 2 times 294 over 3 square rooted. That gives us velocity at point 2. All right, we just solved for v. So we multiplied by 2, divided by 3, and took the square root. So I'll take 2 times 294 divided by 3. Flip my phone on the side so that I can find the square root, and that's 14. Is equal to 14 meters per second is equal to the velocity of this spheroid, this ball, as it rolls down the hill. And then we can repeat the same process for KE3. We just take 588 and we solve it the exact same way, and we'll get a different value. All right, so that is how the basic conceptual, how we can take our conceptual knowledge and turn it into solving these different equations. All right, so that was part 2 of the video. If you have any questions, email me, call my office. My office hours are, of course, much more reliable. But have a great day. Goodbye.